Oh, I just closed my whiteboard, for God's sakes. Okay, this is the 8th. And we're going to do section 5.2, which is the volume of the solid of revolution, it's called. So I'll write that. Solids of revolution. Sounds political, but it's not. Volume. Calculating the volume. And we're going to use the, it's called the disk or the washer method. And that's the only method we're going to use. We're not going to do section 5.3, which is called the shell method. Because that usually takes another couple weeks because the techniques are slightly different. It's confusing. So I thought, no, we could do it with just one method. That's fine. Will be enough for us. So we're using, and then also we're going to review today for the midterm. I just erased that right as I was turning on the recording, so let's put it on there again. So this kind of situation is like we already did, finding the area under the curve or between curves. So let's say here's a kind of simple one would be y equals the square root of x. And if I wanted to find the area under that curve, we know how to do that. We take the integral of the function. But now we're going to step it up to revolve it. We have to know what axis we're going to revolve it around. So we start with going around the x-axis. And we still need like an interval, an a from A to B of where we're going to look, because these would keep going, but we define it so it's finite. So there's an actual volume, and then it's like that blue part of the curve is spinning around the x-axis like that, and then it makes a shape, and we fill in. Oh, good, Angel's back. We fill in the shape, and so it's a solid. And it isn't always. Sometimes we make other kinds of funny shapes. I'll show you. But in the beginning, we just start by thinking of it as a solid chunk there, almost like a flower vase on its side. This one is. I'm trying to think of what other kinds of things have that shape. And this is useful in a lot of fields in engineering. It's also in medicine. Like there's one problem where they approximate the volume of a liver and things like that. But of course, we have other technology to do those things, but it's kind of interesting. So when we picture this now, instead of those rectangles, we have these slices, kind of like a CAT scan when it shows slices. And if you took out one of those slices that I just drew, it would be a disc. It's not perfect there, but it would be like that. Like the one video that I posted, this guy had these CDs he holds up, which is a really good example. So just an infinitely narrow disc. So we end up having to find the volume of a single disc is, if it's circular, is pi, the area of the circle, or the area of whatever shape you have, times the height. But it's on its side. So really, if I turned it over and just take the same disc and lay it flat, there's a center. It wouldn't be quite that thick, but the volume here, the height is that little bit right there. And we're still talking about as as delta x gets close to 0, the same kind of idea that we've been talking about before with those rectangles. So if we could get it infinitely narrow, like thinner than a hair, then our volume would be the most precise. So we end up going, so the volume of any cylinder is pi r squared h. But the volume of our whole solid, so this one I just went off the cuff with this. F of x was root x. Let's say I'm turning it into an example. It's around the x-axis. They have to tell you that part where it's spinning, because it could spin around the y-axis too. And then let's say we want to go from the interval 0 to 9, because square root of 9 is 3. So if this was 9 right there, and that's 0, that would be, I kind of built the problem around the picture so we'd have something to look at. And then I'll write it up here. So the volume of this shape would be the integral from 0 to 9 of pi r squared dx. But don't copy that down yet, because what's r? Like, we don't have r in our problem. So we have to look back at our picture and think, okay, the radius is from the center to the edge of the disk, center to the edge of the disk. Let me make it in black. Okay, if I was here, up to the edge. At any point, it's going to change as I go along, but that's right there is the radius. So the radius equals the function value. If you're doing f of x or g of x or f of y or g of y, the radius is just the value of the function. So we'll stick this in here correctly. So from 0 to 9 on the x-axis, everything has to kind of relate to x. And this was the f of x was square root of x. That was the function value. Square it, because it's a circle, area of a circle, times the width. So we just write it delta x, or some people don't. I always tend to go to delta x, but you could just say dx also. So that would be our volume from, okay, did I get it all in there? Yeah, 0 to 9, and that's on the x-axis. Pi r squared turns into pi square root of x squared times dx. So everything, it's all about the x in this one. So if it was the other way, everything would be in terms of y's, but we're doing this one this way first. So we could go ahead and calculate this one, but I'll go to another page. We also can like verify the volume of a sphere using this method, which is kind of cool. And there's a lot of different things we can do, but I'm just trying to stay on topic here. 0 to 9. Pi squared of x squared is just going to be pi x dx. That's it. So then we can take out the pi to the front because it's a constant. 0 to 9 x dx. Then add 1 to the power, put 2 underneath, go from 0 to 9. So it's going to be pi times 9 squared over 2 minus 0 squared over 2. So it's 81 pi over 2. Or sometimes they'll write it, either way is fine, that way. So that's the volume of that region, that shape, solid. The volume equals that. And then like before, we would say cubic units in real life, but in these problems on the graph, we don't. We just put the number, 81 over 2 pi. We can go the other way too for the whole thing. I'll show one like that also, but let's do my next example. So example, this is the official examples, let's say. I'll call it 2 though, because we already started. So here they'll say, find the volume of the region defined by y equals x plus 1, y equals 0, x equals 0, and x equals 2, about and rotated about the x axis. So it's very much like when we were finding the area of a region. So now we're just going into 3D. So we, like before, we want to sketch it. I'll put it over here. Because already I could see these are the boundaries of the curve. So x plus 1 would be y equals x shifted up 1. So 45-degree angle should be about like that. And then y equals 0 is the other boundary here. So they're handled. This is going to be the one that'll define our radius. Then we want to go from x equals 0 to x equals 2. So we're talking about taking this region like a little flag kind of and spinning it around the x-axis. So when we spin it and we go ahead and sketch it, so it's going like, that's what I would bring a little flag usually to class and we practice spinning. So it's going to spin that way around and just extend the image symmetrically. So this would go to -1. That was 1 right here. And then this would angle down 45 degrees. And then it's 3-dimensional, so it would look more like a truncated cone, like that. And then this, if I turn it, I could turn it sideways again, but that's kind of what it looks like. Let's turn it so it's oriented the right way though. Then we sometimes kind of shade it in or whatever works for you. And then it's solid all clear through in this case there. And like I said, there are times when it's not, when there's a hole in the middle, we'll do something like that too. But this one would look like that. So that's our shape. And then there's like in the dimensionality, there's this back part. If you could see through it, there'd be there. So then I think it helps to just go, okay, it's in terms of x. So it's going to be dx at the end of it. The boundaries or the interval of integration is, or the limits of integration is on the x-axis. So that's cool. The r, the radius that we're going to use is this top one. That's the radius of each disc if we were to cut them up into discs like CDs. So that's going to be r. I'll write it right here. So we're going to use, for the radius, it's going to be x plus 1. So for pi r squared, the area of the circle, r squared is going to be x plus 1 squared. And if we FOIL that out, x squared plus 2x plus 1. So this one's a tiny bit trickier, not too much yet. I'm trying to keep them not too crazy tricky because we just are blazing through the summer course. So the volume is going to equal pi r squared. So I'll put the limits of integration, pi r squared. And like I was saying yesterday and the day before, it's the little details that trip people up. Like they'll forget about the pi or something like that. Pi r squared times the width, so that's the dx. So there's the setup for our volume. And like I said before, we'll go to the next page and I'll pause so you guys get a chance to work on these. But I'll go to the next page and show you, just to remind you, put pi out to the front, and then that keeps you from forgetting about it, kind of, I mean, but you don't have to bring it through to every term. That would make it more work. And then I just double checked here because I'm a little tired today, and that's the kind of thing, like I would write the wrong number or something like a 4 for no reason in these sometimes. So I always have to, so I know myself the kind of things I do and double check stuff. So we've got pi out front, and then x squared plus 2x plus 1 dx. From 0 to 2. And then remember, I think Angel was looking at some videos where they do each one separately. If anybody likes that method better, that's fine. I think it's a little more work, but maybe that's just me. You know? So you could always break it up into single terms if you ever want to do that. But now here I'll pause and let you work on this one. We'll go through it. We've got let's see, pi out front, x cubed over 3 plus 2x squared over 2 is just going to be x squared, and then this is x from 0 to 2.
Oh, so the 1 turns into an x? I thought the 1 just got dropped.
Oh, no, because 1 really equals 1x to the 0.
Oh.
So we add, there it is. 8/3 plus 4 plus 2. There it is. Well, that was easy to find. And 6 equals 18/3, so that's why it's 18 plus 8. Angel, are you still there? Never know with that guy.
Yeah, I'm here.
Okay, just kidding.
I heard that. Come on. This isn't like last semester.
I know. You've been really great. All right, so here we could also use this, like I was just saying, verify the volume of a sphere before we do one going the sideways way, or a funny shape of a sphere. So the formula for the volume of a sphere is 4/3 pi r cubed. Excuse me. So that's just the formula that we tell people. Here, memorize this. Well, I'll show you. This is where it comes from. So if we have a half circle like this, I'm gonna make it pretty easy. Let's say that's a semicircle with a radius of what did I have here? Radius of, let's have the radius equal to so if it was a full circle equation, if the radius is 2, I'm making it harder than it had to be. Jenny, what are you doing? Oh well. and carry on. So the radius is 2, and this is up to 4. If radius is 2, and we are going to turn it into a sphere, we could just plug in the 2 into the formula and we would have the volume. But I'm just going to show you that we can do it this way too. We could say that we're going to rotate this curve around the x-axis. So it's going to come here. And let's see the formula for this circle. The circle before it's a solid, the circle equation would be x, its center is at 2, 0. So x minus 2, 0 plus y minus 0, 2 squared equals the radius squared. So the full circle formula is that. So this would be x squared minus 4x plus 4 plus y squared equals 4. And then when we get y alone. So y equals the square root of, I'm just going to throw everything over to the other side. So subtract 4 from both sides and they're gone. So y equals negative x squared plus 4x square rooted. So the y, if I was going to put this like in a TI calculator to graph it, I'd have to do all that to get y alone. And that's the function value. And that would be the r that I'm going to use. So I'll show, I'm just going to set up the integral for this one and then let it slide. So this would be, if we're just looking at the top half, whoops, come on back. If we were just looking at the top half of the circle, we could say that y equals just instead of plus or minus, just the positive one, negative x squared plus 4x. So r squared would equal negative x squared plus 4x, because we square a square root and it would come off. So we could continue this, and like I said, I won't go all the way through this one, but it's kind of fun to just be like, oh, so that's where that formula comes from. It's so exciting. So the volume would be, in this situation, we're going from 0 to 4, because that's where it's hitting the x-axis, and those are on the x, and then pi r squared. It's a little harder than the one I was practicing in my notes, but it would still work. So it should end up coming out to be 4/3 times pi times the radius was 2. 2 to the third is 8. So it should come out 32 pi over 3. But we would do this one that same way as the last one, just do the integral and then plug in the values and see, etc. So there's other ones like that too that they can use. We can use this method to verify our other formulas. I was gonna move right along, but let me do one like this. So another example. This is kind of example 4. Here we go. So y equals, this will be interesting, x to the third, y equals x. X is greater than or equal to 0. And then we're rotating it about the x-axis. This one's still all in terms of x, just so everybody gets a good feel for it. So it doesn't tell us the limits of integration other than that x has to be greater than 0. So go ahead and sketch it. Or use your graphing technology if you want. And take a little minute to try to go ahead and sketch it. See what it would look like when you rotate it. And then we'll start setting up the integral. This one's a little harder. This is number 7 in your textbook in section 5.2. So I know when y equals x, we've got, if this is 1, maybe make it even bigger. Here's 1, here's 2, here's -1, -1. So when x is 1, y is 1, etc. So that's the y equals x, how it would look. And then y equals x to the 3rd. Remember, that's that Arzuzecha shape. Doesn't bump down quite that much in this situation. But when x is 0, we could already tell maybe that this is where the action is going to be. When x is 0, y is 0. When x is 1, y is 1 for this one too. So right away we could tell, oh, because they said we're looking at x greater than or equal to 0. So there's all this, like, it's almost like code or secret code, I think. All the things you have to pick out of there. So it's going to be between those 2 points. And where does our Zuzecha look? Kind of like this. It would be coming up from here, but we don't care too much about that. And then up here. There. So that's pretty much how that would look. And then we're really interested, like I just said, not this stuff. So I would erase that if I had just put it in here with a line drawer. I don't want to lose my whole line. Anyway, so this is our shape. So remember, like in section 5.1, we could find the area between those, that yellow smile, and leave it at that. So we can use integrals to find the area. We would take the top, look at which one's the top curve minus the bottom curve, and take the integral from 0 to 1. So just for a quick review, so we'll put that up there. So if we had to find the area, that would be the top one minus the bottom one from 0 to 1. So we could do that for that, just for that region. Sometimes they'll put this little r, area of the region, but they also use that little r for right-handed and left-handed area calculations. So I don't know if I should even put r, but the area of the yellow region would be that. Okay, and so the rate now, if we rotate it, if you've already done this part, that's great. I'm gonna draw something symmetrical down this way. And this would also be like that. Almost looks kind of like a flower. And now we would spin it. So if we're spinning it, it would comes like a circular shape like this. And so this is one that would be, the outside would look like those black lines. The inside would have that little opening there like that. And it would be also convex on all sides, but kind of slope down in there into the, almost to the base of it. See? So that's what it would look like. And so a picture like this, not perfect, but that's all I'm looking for from you guys. Nothing more wild than that. But even that, I don't know, I think it's a little hard sometimes in the beginning with these to get used to all of the things. And now we also have to notice, because we're going to do the volume. So for the setup of the volume, we need pi r squared, remember? So the radius in this one is the top function minus the bottom function. Just like that. So r squared would be x minus x to the third squared. And so that's where it can get to be a bit of a task, because now our volume would equal, I'll put pi out front, pi r squared. And our x values was 0 to 1, the place where that action is happening. It's from 0 to 1. I'm trying to think if, you know what, there's an easier way to do this. Let's do it. Let's do the easier way. This would work, but I don't want to make it any worse than it needs to be. There we go. So the radius of the top, if we just were looking at the top curve, the radius, if we spun that top straight line around, would be x. So radius top squared, that's a t, would be x squared. Let's do it that way. That'll be easier. And the radius of the bottom curve that we're kind of cutting out of our situation is x to the third. So a radius of the bottom curve, the circle that it makes squared, is going to be x to the third squared, which is x to the sixth. There we go. That'd be much easier. So let's fix this down here. Pi r squared minus pi x to the sixth dx, 0 to 1. There, and I'm going to pause it again and see if you can get that integration okay. Waiting to see how everybody's doing.
Or pi over 21.
Awesome, Miles. Yep, that's it. Good job.
Thank you.
Any questions about that, anybody? All right, so to be fair, I have to do at least 2 going the other way. They're not my favorite, so I've been making myself practice them a lot because they just feel so weird, but it's the same idea, but we have a relation in terms of x on that side. So we're going to find the volume, first sketch, then find the volume of the curve of the region defined by those 2 curves. That's how we'd say it. And then from the interval is going to go oh, they might not tell us. Oh, yeah, they tell us. For number 5, x equals 0 and y equals 9. I'm trying to copy it just how they have it. No, I was writing it from my notes. So it already gave part of the answer there. So there's all we know about the y-axis. And I don't know a lot about engineering and machinists and stuff like that. And I imagine when they write programs to create objects and stuff that are circular or spun like on a lathe and stuff, that this would be useful. I don't know if it's, I mean, my cousin's a machinist and And he's like president of his company. He never got a bachelor's degree. So I don't think it's like required, but it must be for some things that people do, you know. But this whole idea of this envisioning stuff three-dimensionally is so good for us. And we're doing this here, and we do it in Calc 3. And that three-dimensional reasoning just bumps us to the next level of thinking, I think. And so being able to turn them sideways is helpful. And of course, Desmos, you can just pop it in there and it'll show the whole thing. But I like to try to make myself do it by hand. Like if I had a table, if x equals 0, so I'm doing this curve, wherever x equals 0, it's this whole line right here. So this is my x equals 0 line. Where y equals 9, let's say this was 9 up here. Over, we've got that straight line. And then 2 square root of y. So if y was 0, 2 square root of 0 is 0. So when y is 0, x is 0. When y is, let's say, 1. When y is 1, let's say it's here. X is 2. So we're there. And we could start to see that it's going to be this shape, which is, it's almost like half of a parabola. There. So, but you can just put in points. So at 3, when y is 9, x is 3. So that's enough, like making a little bit of a table. 2 square root of 9 equals, oh no, 18. My bad. It's going to go back it up. So see what happens when you do it by hand? It doesn't always work. There you go. So when y equals, let's say here's 4, x also equals 4. You go like that. So it's a little more curved than that. It's like a parabola. There. Wait, I think I'm curving it. I'm really struggling. Here, I'm going to stop this a second and fix it again. I have it on my paper and I keep messing it up this way. There. Okay. All right. So this is what I was saying. They're trickier to me, but I should be a little more careful here. All right. So now we're spinning it around the y-axis. We could see that even though they didn't tell us, when y equals 0, that's one of the limits of integration. And y equals 9 is going to be the other one. So we already know we're going from 0 to 9 in the y's. And I have to keep reminding myself that we're doing everything in the y's. And then when we spin it, we go spin around the y-axis. Let's come back. And this one doesn't have any kind of hole in it or anything because it said just x equals 0 was our boundary. So the original region was this here. And then we spun it around that way, around the y-axis. So there we go. So let's set up the rest of the integral. The radius is going to be this here, that x value. So radius squared is 2 root y squared, which is a lot nicer to integrate than a radical, although we can. So the volume is pi times the radius squared. We could say minus 0. I'll just put it in there, but it doesn't really matter. So dy minus 0 dy. Because even if I put an x on it, if I go, okay, that's 0x to the 1 when I do the antiderivative, that'll just equal 0. So that'll just go on because of the 0 part. But it's officially in there at first. I'm not going to require that you show that. If you understand that, okay. And if you don't, just stop me. And we'll go to the next screen to finish that. I'll just wait a second. I hate every time I restart the recording, it says recording in progress. So I'll just keep it recording. And then, like I was saying before, the limits of integration are in terms of y. The function is in terms of y. And we're spinning around the y-axis. So all those things correspond together.
It's 162 pi.
Yeah. Good job. Very nice. Okay, we're gonna do another one this way. Do you guys have any questions though?
Not really. I'm just taking notes on how to do most of the stuff. I'm not really trying to do it myself.
Okay.
Honestly, I can start trying some of them if you want me to, though, Jenny.
Well, whatever works for you, Angel. If you're okay doing it this way, that's fine too. So let me see. Here's another one going around the x-axis. Oh no, I don't want to do an x-axis. Let me find where's my other y-axis example. Oh yeah, number 9. Well, that's gonna look a lot like the one we did before. Hold on, I'm just gonna pick a different one. Here we go. Okay, so let's look at, this is number 10 from the book. If we had x equals 2 minus y squared, a little bit harder one. So the language again that they say is find the volume of the solid obtained by rotating the region bounded by the given curves about the specific line. Sketch the region, the solid, and a typical disk or washer that would result. So here, this one will be a little bit trickier. So the 10, x equals 2 minus y squared, and x equals y to the 4th. That's all they tell us. And we're going about the y-axis, find the volume. So now we've got to, remember in the area problems, if it's a sideways one like this, in terms of y like this, then we take the area on the right minus the area of the left, the right-hand curve minus the left hand. Instead of top minus bottom, we always do right minus left. So that's an important first step. And again, we want to sketch it. So I'll pause again and see. I better make sure. I haven't done this one yet, so I'm gonna make sure I have the right answer too. So I will just pause. I will pause the recording here. I'm going to mention here too, we did a couple like this with the area problems where we find the limits of integration using algebra. I'll just remind you, if you take one of the relations and set it equal to the other one, That's how we can get our two y values exactly if we're not sure, or if the graph isn't totally perfectly clear that this one's -1 to 1, because we're just looking at that little yellow area spinning. And thinking about what that would look like. So if we get everything to one side, y to the fourth plus y squared minus 2, then we factor it. So this is if you don't have graphing software and you're just freewheeling it. -1, I think it'd be y squared plus 1, wouldn't it? Oh, plus 2. 2 times -1 is -2. 2 minus 1 is +1. Yep. So if we set each of those equal to 0, y squared equals 1, so y equals plus or minus 1, and y equals -2. And that's irrelevant for our picture, so we don't go outside of there. So we're just going to use negative and +1. And that's why I stuck those there. So those are the y limits of integration. And then the right hand one is going to be, the volume is going to be pi times the right hand curve squared minus the left hand curve squared. So that will be to the 8th. Forgot my dy there. And that should work. The answer to this one is 248 pi over 45. So I'll give it another minute, because I didn't, like I said, I didn't do this one. I did some other ones that were kind of not as exciting. Let's see. So we have to FOIL out that left hand one.
Where is the y to the 8th come from?
Oh, that was taking this one squared. Because
Oh,
so the r is going to equal that. The r squared is that squared. That's squared. And so when we spin this around the y, it'll look like kind of like this, with the top sort of open. And then I think, let's keep going, keep working on it.
Can you combine like terms in the parentheses? In the integral?
Yep. There aren't any like terms. I made a mistake right here. So there aren't any like terms right there, but later you can, yeah.
Oh.
So I'm glad this happened in this one too. It should work out now. But if that ever happens, if you're like, did I mess up my signs? It all zeroed out. How could that be? It's probably because part of it's on the wrong side of the line. Half of it's on the opposite side of the line. It could happen. I mean, it could happen that we make a mistake with our signs too. I do myself. So this one should come out once it's set up like this. It's 248 pi over 45. Do either of you want me to go through the steps of that integration, or are you okay?
Maybe just the differentiation. So we can teach it.
Sure.
So it should be
Right here. Yeah.
y minus 4y to the third over 3 plus y to the fifth over 5 minus y to the ninth over 9.
Yes. Good. And again, this was number 10 from the textbook problems. And this is, I forgot a y right there. I think I got it. Yes. And then I'm going to go ahead through it because why not? Because the zero, and this makes it so much easier because we don't have to do a whole minus anything in brackets because it's all going to zero out in this case on the second step. 4 times y. And these are mostly pretty straightforward. And then we need a common denominator, which would be 45. And 4 times 45 is, so I'm going to make each one go to that common denominator. And then 3 times 15 is 45, so 4 times 15. And 5 times 9 is 45. 9 times 5 is 45. So that's how we can get the numerator. And it ends up to be 2 pi times 124/45, which we don't have to reduce that or turn it into a decimal or anything. Just finish it up as 248 pi over 45.
Looks good to me.
Okay. Alrighty. There are story problems with these two. I think, let me check the Moodle. I think I wasn't.
For a minute.
Yeah, we'll take a break for 10 minutes. So
Perfect.
come back at 10:30. I'll
Okay.
check the appointment. Okay. Okay. One more that's an application problem and helps us review the midpoint rule with the rectangles that we did in the first week. So this, I like this one. I think this is in the book. It's number 45 in section 5.2. So they show the region if it's rotated around the x-axis to form a solid, use the midpoint rule to estimate the volume of the solid. So with n equals 4. So first of all, we go, remember that b minus a. So delta x. So this is a nice little review. Then I'll pull up the review sheet and we'll kind of talk through it. So that right endpoint minus the left divided by, they said, let n equal 4, which is, I like this one because it's not too long of a problem. 8/4 is 2. So each rectangle is going to be a width of 2, or delta x will equal 2. So when we do the same kind of formula idea, but a little bit of a throwback to the rectangles. Did you say something? Are you okay? So these are the intervals. We should have 1, 2, 3, 4 intervals. And the midpoint rule says make the height of your rectangle the height of at the midpoint of that strip. So that would be, remember, that would be strip 1 if you wanted to label them that way. Here goes strip 2 is going to be this height. The only problem with this one is that estimating. What's that y equal over there at that point? So that was a little bit of a pain for me, but you're just doing these. If you do this one, it's in the, so I'm not going to do the whole thing, but it's for extra credit in the assignment. I just wanted to remind you how to do those midpoints when you're doing them by hand. And then here's the midpoint of this interval. It's that high. So if we were just finding the area under the curve, we'd add up those areas of those 4 rectangles, and that'd be it. So the area would be the sum of those 4 rectangles or strips. And there's some wiggle room, like I said, with this answer. Like, I'm not going to put one like this in the midterm because it'll be on WebAssign, and it's hard to get I can stretch out the margin of error, but sometimes even then, I don't know, I'd just rather see people's work on these. So these people, I'd like to do these on paper. I assign them this on paper. Anyway, so don't worry too much about the amount, but I would say the first height is, oh, so hold on. So remember the height of the curve at a certain place was our radius if we're talking about the volume. So the volume is going to be pi times the radius squared times that dx amount. So that was 2, that because they told us that. And then pi had just dropped down. And then for the radius squared, we're going to take the height of each one of those and square it. So I'm just going to write the height of the first one. To me, it looks about like 1.5. The height of the second one, maybe 2.3. So I'm just getting those by looking over here at the y's. The height of the next one, maybe 3.8. And that's what I mean. Like, this kind of problem bothers me when I'm a student, because I'm like, what if I'm off by 1 decimal point in this kind of guessing game here? I'm not a fan. But then this height the third height is 3. I mean, the fourth height is 3. So the volume is going to be, remember, the 2 times the pi times each of those r squareds. I'm going to put it up here so I don't change screens. So the volume is going to be 2 times the pi. And we don't do a summation or a sigma or anything like that. Just jump right in and take the 1.5 squared, the 2.3 squared, the 3.8, and the 3. So mine were a tiny bit off because my answer is 1.4 units away from the correct answer according to the book. So that I'm going to leave it there because that's one of the I think I put it as it's one of the extra credit problems. So if you want to finish it for extra credit, power to you. And then I put in 2 other problems like this one with the midpoint rule. And so just remember these steps, and this is, we can review this again in a minute, but that delta x is always the right end minus the left end divided by whatever they said, how many rectangles they're looking for. So this one is not the closest approximation. Like if we made more narrow rectangles, it would be closer to the true volume. I mean, true area and volume. So does anyone have a question about that? So it's, we don't have time to do a whole lot of these story problems, but I just wanted to do at least one that's a little bit of a story problem. All right, now I'm gonna log in with my other device and pull up the review test. There it is. I was like, what day did I put this in? For day 6, the practice test is here. So I just wanted to make sure you guys knew where it was located. And then there's some more videos that I just pulled up, but it depends on what you like, what kind of YouTuber you like. This kid, that was the first time I've seen him before. I mean, so I thought his was pretty cute. So really enthusiastic. So this is the old test, the old midterm that I used the last time I taught this. So I like to just use that for studying, but your actual midterm will be on WebAssign. I'll just put it in there, and I'm gonna, like I said, not have too much of the ones where you would be drawing them where I'd want to see the pictures. So I just had that in last week's quiz. And if anyone ever wants to redo their quiz or do a similar one for a better grade, just let me know. I'm not putting you guys on the spot. That's just for anyone in case they're watching. And let's make this a little bigger. So, not that big. There we go. So this one, the first one, sketch the curve for f of x equals negative x squared plus 4x plus 5 from x equals -1 to x equals 5. So of course, if you're using graphing software, that shouldn't be too tricky. And so it'll be a parabola and it'll be cupped down. And we could do this using algebra and factor it and figure out where it's going to hit the x-axis. But and it does hit the x-axis at these two. So that was the, so what I would do if I'm putting that on the midterm, something like that, it would be one where you pick from the 4. And you have 2 chances, so. And then this, like I just said, I'm not going to put one like that on the midterm. But I mean, maybe where you just pick, like this is the one where the rectangles are in the midpoint rule method, like I just showed. Or remember, the top of the rectangles could be, it could be the right top or the left top or the midpoint. My favorite is the midpoint method, but I mean, it just depends on the curve, which one works the best. But we should probably go through one like this back on the whiteboard if you guys want, or you can just work on it and then we can go over it tomorrow or individually.
Well, I wouldn't mind going through one of them.
Okay. Yeah, let's do that one. We'll do that one. But I'm going to scroll on through. Then I asked them to do the definite integral of that same curve.
Your whiteboard is all frozen, or your screen is frozen.
Oh, well, thank you for telling me. I stopped the share and restart. I probably picked the wrong share screen. There we go, here.
There we go.
Thanks, Miles. Okay, then it went on down to finding the definite integral using that same function and asking whether or not they expected that answer. So you might see something like that in WebAssign where you do both. Then number 2 is one of those displacement problems. So we can go through all of these for sure. Let's see. So this is where, remember, the velocity, if we're finding the displacement, that's the integral of the velocity. And then the distance traveled was altogether the absolute value of the negative and then added to the positive distances. So the left and the right. So we can go through any or all. Let's just look at all of these. This one is more of a thinking problem. So the rate at which the world's oil is consumed is represented by R of T. T is in years, starting at T equals 0 on January 1st, 2000. And R of T is in barrels per year. So we're talking about the integral of a rate. So just like the integral of velocity is position or distance. So the integral of a rate of oil consumption would just be the amount. So it comes up to being the amount of barrels. From 0 to 18 would be from 2000 to 2018. So this, you don't calculate it. I don't think, no, I didn't ask for the amount, just to, what does that mean? It must have been like, I must have copied that wrong because it must be like more than just barrels per year. I'll look at that again. That's that I pulled from the book. Then these are practicing some definite integrals. This is a regular one. This one needs U substitution. And this one can't happen. This one doesn't exist because when x equals 0, the function's undefined, but the limits of integration went across 0. And so that can't happen. So that's the one that doesn't exist. I'll probably have more definite integrals in there just because that's easier to assign them and do your answers in WebAssign than here. This one was a U substitution problem, D. And so is E. I mean, E, you could expand and do it term by term, but it would be a big bunch of terms. So again, I'll go back up to the whiteboard and do a few of these and maybe some before class tomorrow if anyone wants to work on them themselves first. So these two, we might have even done this one today. Find the 2 points of intersection where the curves intersect, and then sketch the curves and shade the area between them. So we've just been doing that this week. And then estimate the area using just like length times width or some kind of whatever shape it looks like to you, circle. And then determine the exact area between the curves using our integration method. And then find the volume of the solid that results when the regions rotate about the x-axis. And that's what I mean. I'm only going to put one volume problem on the test because I just don't feel like we've had enough time to really digest it. Even me. No, just kidding. And then here's the average value. We did that with section 5.5. And so that was the formula 1 over b minus a times the integral of the function. So those are just calculating more integrals, honestly. And again, we can do a couple of those too today. And I talked about this yesterday in class. And I said, I'm not going to ask you to find C in this to find that where F average equals F of C. But I explained towards the end of class what that means. So I won't put one on there like that that's asking you to find C. I think I put one on the assignment though, on the homework. And then this one is also an average value problem. And sometimes people struggle with this one. Let me see why. I think it's because of the time. T hours after 9 a.m. Yeah, so we don't use 9 when we do the integration. We're going
Use 24 hours, right?
Yes. Yeah. So, actually, this one's only from 9 a.m. to 9 p.m. Yep. So we're just going 12 hours. So just looking at that carefully. I know that's from the book too. So I remember doing that other semesters, not with you guys yet, but I remember people struggling with that and bringing it to class, and we had to go back through. Oh, and we also had to make sure we were in radians up here instead of degrees. Maybe that was no, we put in hours. It wasn't at radians. Yeah, it was some other weird thing. So we might want to go through that one today too. I don't know, to see how much energy we all have, huh? So that's there. That's available on your Moodle, and I think I might have emailed it out too. But let me get my whiteboard back up and see what we can do here. Oh. All righty, here we go. So back up to the top. If we're doing negative y equals, so this was problem 1. Sketch the curve for f of x. Equals negative x squared. Oh, I'm going to do a couple of the hand sketching techniques. So first factor out -1. And then factor this will be x minus 5, x plus 1. It's going to equal 0 when x equals -1 and x equals 5. This is just a tiny bit of review of intermediate algebra. And we did it in college algebra too. So I already know it's a parabola cupped down. That was a terrible picture. It would not look like a seashell. So, and it's going to cross the x-axis here. And we also know, quick review, the best way to find the maximum point. I mean, I already know it's a parabola, so it'll be symmetrical. 1, 2, 3, 4, 5, 6. 1, 2, 3. So I already know the high point is going to be when x equals 3. So honestly, I don't even really have to find the derivative because I know that it'll be the same on both sides. But let's just for the sake of the picture, when x equals 3, f of 3 would be -9 plus 12 plus 5. So 17 minus 9 is 8. Just make that be 8 so it fits. And if I was doing this for an assignment, I would do it on graph paper, so it would be a little bit more precise. So when x is 3, y is 8, that's enough to get a nice curve going here. So the question said, go ahead and sketch it from x equals -1 to x equals 5. So I would just kind of highlight the part that we're interested in. And then did I say to shade the region or not? Let me see. No, I didn't say to shade it, but you could shade that region too if you wanted. So show how to find the Riemann sum for this situation with 6 subintervals. So n equals 6. So we're going to take the right end minus the left end, divide it by n. So delta x equals 1. So there's our intervals 1, 2, 3, 4, 5, 6. So double check that 6. It's going to be 6 rectangles. And I said use the midpoint rule. So the midpoint of each interval is where we're going to take the height. So the height here, and then I'll draw the rectangles next. The height here. And I'm just double checking every time, make sure I've got 6. So this my first rectangle, second rectangle, those should be exactly the same height if it was perfectly drawn. Same with that one. That should be lower. Okay, so that would be S1, S2. And then the width of each one, delta x, equals just 1. So area equals the width, the height times the width equals the height times delta x for each one. And we can, I don't require this part, but we can put the sigma here. Go from 1 to 6 rectangles of the height of each. So s to the n, oh, this should be n. S to the n dx. That's what how we would write it in the Riemann sum form. But I'm just looking for figuring out what those areas are. So let's see. The first one looks like the heights are, oh, we can find them exactly. So let's do that. I was going to estimate like in that last picture, but no, let's do that exactly because there's only 6 of them. So f of x equals negative x squared plus 4x plus 5 is our function. So the first one is going to be f of a half. The second one, these are what we're going to put in here. I'm not going to do all those, but f of 1.5. So, but here we can get it exactly. So it's pretty, it should be pretty good. It still won't be as good as an integral because there you could see those rectangles don't perfectly cover it. F of 4.5, so halfway between the endpoint of each interval. And what did I forget? Oh, backing up here. Negative 0.5 because we went across to the negatives. So here's S1, S2, S3, S4, S5, S6. There. So we're going to make sure there's 6. So that's where I just almost forgot that one over there on the left side of the y-axis. And then we can get the exact values since my sketch isn't so perfecto. But remember too, like I was saying, these, because it's symmetrical, it's a parabola, the first and the last height will be the same. And the second and the fifth will be the same. And the third and the fourth. They should be exactly the same. So we really only have to find 3 of them and then double it really. So we could do that. So I'm gonna go ahead and do it, but I think I plugged in my, oh no, here it is. Negative 0.5 squared minus 2 plus 5. So the first one is 2.75, the first and the last. And then if we go ahead and put in 0.5, there we go. Negative 0.5 squared plus 4 times 0.5 plus 5. So the second one is 6.75. There's still the 2 in the middle, so let's get that. Negative 1.5 squared plus 4 times 1.5 is 6 plus 5. So 8.75 is also in there, 2 of them. So the area is all those times delta x, which is 1.
$73 halves.
Yeah. Yep. Excellent. Keep it right up. Sometimes I wonder, are they still here? Because when I'm on the whiteboard, I don't always see your pictures. Sometimes I close them so I have room. Great.
Oh, sure.
Good job. All right, then. So then it says calculate. Let's do the definite integral and see if it's close to that. So we're going from -1 to 5 of negative x squared plus 4x plus 5 dx. So we've got negative x to the third over 3. 4x squared over 2 must be 2x squared. 5x 5 negative 1. So we do have to plug in all those values, but that's all right. 5 to the third is 125. And then 25 times 2, 5 times 5, minus, then I always put this big bracket, -1, negative of -1 to the third is going to be positive 1/3. And then 2 times -1 squared is just 2, and 5 times -1. Yeah. All right. And then combine kind of like terms, -125 and -1. And then 50 minus 2. And you could do more of it combining, but 25 minus -5 is positive 30. So I've got 78 minus 126 over 3. Might as well put 78 over 3, 234 minus 126 equals 108 over 3, which is about, oh, that's exactly 36. So that's the area under the curve exactly. It's 36 units, 36 square units. And backing up here, look at that. That was only not too far off. 36 and a 2 into 73 is 36 and a half. So the answer would be, oh yeah, that one came out pretty close. So that's that one. Let's do the displacement problem too. Anybody have a question on that though? I didn't rush through it too much, did I? Number 2 gives us the function of this particle, f of t equals t squared minus t, where v is velocity. Oh, I should call it v. I think I was missing a piece there. V is the velocity. So there we go. They give us that. They want us to find it from 0 to 3. So first the displacement, and that's the plain old integral, nothing fancy. That's just like, where's it going to end up at after those 3 seconds? To the left of center, to the right of center, and not how much distance it covered, just where's it at now situation. So that's displacement. That's the easier one. So I won't go all the way through that one, but this would be the setup. And you can have a negative in displacement. It tells you more about, it's also called the position. So it also tells you the position of it, not really how far did it go. But then they ask the distance traveled. On this interval. Find total distance. And then I personally like to just look at a two-dimensional graph. Let's factor our function. Find out where the zeros are. Those are where it's gonna 1, 2, 3. I know it's a parabola cupped up because this is positive. The t squared is positive. And it's crossing the x-axis at those two places. So I don't have to know exactly the y values, just the shape. Here's the shape. Okay, so if I know this one's 1, this is 0, and this was 1, x is 3. This part, I can just do the regular integral. So the distance, let me do that first because it doesn't matter. Is the regular integral, but just from 1 to 3, the above ground, the part that's above ground of the function. Plus, I want the absolute value of the integral from 0 to 3 of that same function. That's what's happening. But when I take the absolute value of something that went underneath, I'm going to turn it negative. So this, the only thing that's really going to happen is this will be negative because that was the underneath part. That goes to negative, and these can go off on their way. There we go. So it wouldn't matter if I wrote the negative one first. Oh wait, but I forgot one thing. Be careful. Be careful, Jenny. This is only going from 0 to 1, the underneath part. So double check. We got the whole thing covered. 0 to 1 is that part. And then 1 to 3 is this part. And that's what they wanted us to go from 0 to 3. So that'll do it. So let's see. I'm gonna go ahead. I'll go ahead and finish this one, I think, just to make sure we're okay. Instead of leaving it hanging. So so total distance is going to be t to the third over 3 minus t squared over 2 from 1 to 3 minus, same deal, from 0 to 1. So 3 to the third is 27 over 3. 3 squared over 2 minus, it just ends up to be a lot of terms. The math isn't hard, but it's easy to mess up and even forget the denominator or something. I put ones in there, 1/3 minus 1/2 in parentheses. Now minus this deal, 1/3 minus 1/2. And then I would put in 0, but we don't have to. That would be 0/3 minus 0 squared halves. That'd just be like add-on work we don't need. So we can just ignore that part. Oops. Make life easier. And then hopefully it comes out really nice. And then the idea though in this shape, I made this as a tool to see when is it underneath and or where is it negative. But we're really thinking of something just moving back and forth or up and down on some kind of line in these problems. So let's put all these over 6, huh? 27 minus 2 plus 3 plus 2 plus 2 times 3. There. 9 times 6. This is if I'm doing it all by hand. I know you guys have calculators or you have software. You can save time and not do it all by hand, and that's fine. But when I do give you paper assignments, I want to see all that work. But this part I'm using a calculator for to save time. Minus 2 plus 3.
By the way, Jenny, I had a question.
Yeah.
Just about the quiz. So you said I could make a correction, or did you want me to retake the whole thing?
You can correct yours.
Okay, because there was like, I got a 16 out of 20. You said something about I could just correct this little mistake and get a 20 out of 20. So
Yeah.
I don't know what it was, but I just remember reading it. I was like at a baseball game and you corrected it. So I looked at my phone. I'm like, I saw the 16. I was like, I was wondering what it was, but I'll look at it more.
Just look at it. I put the feedback on there. It should show. If it doesn't show up, then let me know.
All right.
There's our total distance. So the total was 4 and 5, 6, back and forth, but where it ended up at was a different number. So does that make sense, you guys? And the same with you, Miles, if you wanted to do corrections, you sure can. Evaluating integrals, I wanted to do the one that are 1 or 2 that use U substitution. So let's look at those. And then that, I think there was 1 or 2 more. Oh, that temperature story problem. There we go. So evaluate 0 to 1 sine of pi t dt. So this needs U substitution. So first we'd pick whatever it's sine of, that's going to have to be U. So du is going to be just pi. And to counteract that, the reciprocal of that is 1 over pi. That's what's going to go out here. Backing up to here. If t is 0, the sine of 0 is 0. And if t is 1, the sine of pi is still 0. Oh, what? Hold on, I'll just leave it as it was. We'll leave it in terms of t. So I'm not going to write these values right just yet. Let's just translate it. That'll be faster. Otherwise, we could do the symmetry thing and do half of it, but let's just go like this. So the integral of sine, who remembers what's your integral of the sine?
Cosine?
Yeah, good. So we'll rewrite it as the antiderivative. negative cosine. I always forget that myself. So it's going to be negative. So it's going to be negative 1 over pi cosine of u from what to what. So now let's just plug this back in for u and keep those limits of integration. So cosine of pi t. And then we can do that from 0 to 1. There we go. Which would be, let's finish that up right here. Negative over pi cosine of pi times 1 minus cosine of pi times 0. Cosine of pi is negative 1. Cosine of 0 is 1. So it's going to be negative. So see, these ones, honestly, it's the signs can really make them tricky. Negative 1 over pi times negative 2. So it's 2 over pi. There you go. And again, you can, not against you using software like a graphic calculator should do this for you too, as long as you're in radian mode. If we're talking about pi, it's radians. If it was like 180 degrees, then we'd be in degree mode. So just if you do use technology, just remember your settings. All right. Any questions on that one? That was B on the second page, number 4. Also, like I always say, and if you're plowing through a test, you probably won't do that. I don't know if I would either, but it's good to stop a second and see what it looks like and see if you agree. Does it look like it's about 2/3 under that curve or not? You know. All right, 4D also had U substitution. Remember I said 4C is impossible. 4A is pretty simple. But 4D and 4E, 4D is the harder one, I guess. I don't know. They're both about the same. They're not going to be too wild on your test because, again, I try to put more of the wild stuff in the homework when it's less stressful and you're not under any pressure as much, not as much anyway. So here it might be like, oh no, what the heck? But if I just look at like that one video guy, Professor Leonard, he says, and I think that was really good advice. What's in parentheses, that might be your U right there. See if it's going to work. Let's see, what's du equal? Du dv, the derivative, is 3v squared. All right, so if I changed this to u, du, I'd have this accounted for. There's the v squared. I still have this 3 that I have to take the reciprocal of it and put it over here to keep it balanced. And then all we got to write is cosine u. We consider it like times du. So cosine u du, that got taken care of, so we don't have to write anything about that there. And that's it. Now we just want to go, oh yeah, oh yes, if u was v to the third, now we could change our limits of integration. 0 to the third is 0. And 1 to the third is 1. So hey, they stay the same. So there we go. Now, the integral of cosine, that's the one that stays. It keeps the sign. So it's going to be 1/3 sine u from 0 to 1. And this one, I wonder if I made this one up because your answer is going to come out weird because sine of 1 minus, we know sine of 0, but sine of 1, if we're in radian mode, I don't even know what that is offhand, so I'll have to look that up. So anyway, but it's going to be 1/3 sine of 1 minus sine of 0. And I might have made that one up back then because it's sort of a weird answer. Get that out of the way. I'm just going to see what my calculator tells me is sine of 1. Sine of 1 radian. Very small. 0.017 about. So that's 1/3 times 0.017. And the sine of 0 is 0. So divide by 3 and we'll get that approximate answer. 0.0058. Questions on that one, anybody?
I guess when I put sine of 1 into my calculator, I get 0.841.
Hang on. Are you in radian mode?
Yep.
Oh my God, I wasn't. Thanks, Miles. Corrected me. I was in degree mode. Why not you? My bad. I'm sorry. It's my fault. You get extra credit for correcting me. Very good. 0.841. Jeez Louise. Right when I was saying it too. Well, I won't give one that's a trick like this anyway, because I think I must have made this up that time, I'm guessing. Maybe I got it from the book, but anyway, you can find out what that equals your own selves. Let's do one more, the other U substitution, just to get another one in there. This one's kind of easy. I don't know. I haven't written the test. I mean, I haven't built the test yet, but I have to try to keep them pretty easy. But I don't know if they should be this easy. Again, what's in parentheses is 1 minus x. So we check that. Is that going to work for my U substitution? The derivative of that would be -1. All right, well, that's fine. So I can put 0 to 1. Oops, no, I'm going to change my limits of integration. Put U here to the 9th. So replaced 1 minus x and put du here. And now, since that was -1, that's going to turn my answer negative. Just, it's not supposed to. It's not part of the problem, but it would throw it off. So I balance it by putting a -1 here, just like I do with the reciprocal. That really is like the reciprocal, 1 over -1. So that would be there. And then the limits of integration, if I plug them in there, 1 minus 0 and 1 minus 1. They went upside down like this. So I wonder what's going to happen with that one. Let's do it this way. And because remember, you're supposed to have it, the bigger number on top. I think this one comes out this way. Let's see. U to the 10th over 10 with a negative sign in front. So it's going to be 0 minus -1/10. Yeah, it comes out this way. So this is a weird one. I see. That's why I had put it on there. I won't put any weird ones where you have to go upside down, I promise. So that comes out to be 1/10. Oh, it's just very strange. Any questions on that one?
I don't think so.
Okay.
That was definitely weird.
I don't got anything.
Okay. Definitely weird. All right. We just did the stuff, the number 5 things. So I'm not going to go over that, but I do want to do we'll do just one average value problem and I think stop there. See if we can do both. Let's do both of the average value problems. So f of x is the cube root of x. So I'm just going to write it in fraction form right off from 0 to 8. So f av is 1 over 8 minus 0 of the integral. 1/8 from 0 to 8. And that's it. That's the setup. These aren't too tricky. Just add 3/3 to the power and divide by that power. So we'll have it like this. That's 8. 1/8. And then I'm going to write it back in radical form because it's easier for me to think about personally. But if you're using technology, you might be fine either way with a fraction power. And then we substitute in 8. And then if we substituted 0 for x, it's going to 0 it all the way out. So we only have to do one bit of arithmetic. 3 times the cube root of 8 is 2 to the 4th over 4. This C work. So 2 to the 4th is 16. 16 times 3 is 48 over 8 times 4. And reduce. 6/4, is it 3/2? I think 3, yeah, 3/2. So that's the average value of this function. Meaning if you could add up all the y values in this interval, infinite number of y values going on, add them all up and divide by that many, you would get 3/2. And then that C part that I'm not going to put on the test, where it says show that there's a C that exists that makes this true, you would just find f of C equals C to the 1/3 equals 3/2. So you would just calculate where does that happen. But that's not going to be on the test because I didn't cover that very heavily yesterday or the day before. Any questions on that one? That's more recent material, just in case anybody's struggling, just let me know. Okay, then B, how about, maybe I'll just set this one up. So the average value of this one would be 1 over pi over 2 minus negative pi over 2 of 3 cosine x dx. I'll keep going a little bit. Pi over 2 plus pi over 2 is just pi. And then that 3 could come out to the front because it's a constant. And the integral of cosine is just sine. Is everybody following that okay? And then we've got, I'm going to go ahead and finish it because in case anyone's rusty with their trig, sine of pi over 2 is 1. And sine of negative pi over 2 is negative 1. So it's going to be 3 over pi times 1 minus -1. Whoops. Yeah, that's right. 1 minus -1 is 2. So 3 times 3, 9 over pi. That'd be the average value of that bad boy there. Then it says explain what the average value is. I will put a multiple choice one in the midterm. It asks how, if, so you can pick the answer of the 4 that explains it. And then I think I'll just set up number 9 and see how you do. I haven't even done that one in a while, so you can finish that one tomorrow. Like I won't know if you got the right answer until I do it myself too. So number 9, the function is this: 50 plus 14 sine pi t over 12. Find the average from 9 a.m. and we're starting at 9 a.m. So we're going from 0 to 12 hours on a single day. So t average would be 1 over 12 minus 0 of the integral. This kind we'd break up like this because the 50 is easy to integrate. But the other one is going to need a u substitution. So yeah, I'll keep going and set that up and then stop there and pick up with that tomorrow before we do the test. Let's see, the u is going to be this business in here, the sign of this, because we can't undo that with an integral. So I'll put it up here. U would be, it's really pi over 12 times t. That's the constant part. There's the variable part. So du is just pi over 12. And the reciprocal of that will stick in front of that piece is 12 over pi. And since we see that pi there, we make sure we're in radian mode. Make sure your teacher's in radian mode. And then the integral of sine is negative cosine. So really just, I would take that piece, I would do that part. I'll go on one more screen just so it's really neatly set up. But I'm just going to set up that part, do that one separately. And u is pi t over 12. So again, just this part. And then whenever I do this too, and if you're ever tutoring also with someone and you take things apart to make it look less daunting, just remember to remind them to throw it all back together at the end, which is what like I said, we can do tomorrow. Finish this one up. And du was pi over 12, which makes me have to multiply by 12 over pi on the front. Not yet, that wouldn't be correct. Next level equals 12 over pi times 14 times negative cosine u from 0 to 12. So remember, that's just that piece right here. That piece there, it's still inside this bracket too. So we just, and then when we put it all together, remember this one would, antiderivative would go to 50t from 0 to 12. And then we'd still have to times everything by 1/12 at the end to get the average value. Hoo-ha. Let me go back to that page there. So just that piece. You guys have any questions about that one? That one's pretty wild, and I'm probably not going to put one like that on the midterm either, but we'll definitely have an average value problem. So probably not quite like this one, but
Yeah,
anybody wants.
that one's kind of hard.
I know that one would be a bummer. 50 plus 14. Look,
Ever
done.
likes trig, so yeah. It's kind of
Let's
giving
combine.
me flashback nightmares.
Let me see if oh yeah, I got this one. I did get this one out of the book. The answer is, it's in case you're doing this, I'm not going to go all the rest of the way right now, but if you're doing this, the answer to 17 is approximately 59 degrees Fahrenheit. I'm going to write that next to it so I remember next time. Approximately 59. And we can for sure do this tomorrow before the test if you guys want. We could finish it, or leave it because it might freak people out. But either way, if you want to finish it and send me your work for extra credit, you can, or not, or just let it go. Next it up. So the only other thing we did was, what I didn't have on that midterm for that class was those work problems. So that we just did yesterday, the day before. So as long as, if you've done your assignment before that test, you will have actually done the one or two of the problems that'll be on the test, because it'll just be the same. I'll just take them from the assignment. So no surprises there. Do you guys have any questions on anything?
No, I think I'm gonna just work on my homework and study for everything. So
Okay. And I'll be there early tomorrow to meet with you, Miles, okay?
Okay.
All right. And or if you guys need to meet later, I'll be home after anytime after 4 if either of you need to meet with me for anything, if you have questions. Okay.
okay.
So,
Yeah, that sounds
so the
good.
test is tomorrow then, right?
Yeah, test is tomorrow. We'll just
Oh.
go over if anyone has any last minute questions and then have the test. And I think that's all we'll do tomorrow, just like we normally would in a normal semester. Just have a test day.
Okay.
So if
Okay.
anyone's, I'll catch up too.
Okay.
Okay.
Sounds
Have a
good.
good day.
All
Good
right, thank
work
you.
today. See ya.
Bye.
See ya.
Bye.